And just I was wondering, it may happen another one in November, you know. So, well, let me finish. So, if you guys will agree, one Saturday, we'll come here 10 to 12. You know, like all over those hours, you know. Saturday, 12 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 9, 8 to 10, 10 to 12, whenever you want, you know. One Saturday. You're not from 6 a.m. to midnight, right? It's like 2 hours, you know. Yeah, right? See that you are agreed. I have to make up for those classes. One Saturday, you know. If Saturday is not good for you, maybe we can come, you know, Friday. If I can, Friday, the problem is if I can find a classroom, you know, for the makeup class. And especially the class size of this, I don't know if I can find, you know. I need to start to check with my job. Which one would you rather, Saturday or Friday? Friday. This is the first analysis. May I ask how many of people in the waiting list they got into the class? Just I want you to raise your hand, please. Those one they were from the waiting list. 4, 5, 6, 7, 8, 9, 10, 11. Cannot be 11. How is 11? You went up to Maida and she put you in the class. I mean, you got a confirmation from Maida. She said you are in. Just want to make sure you are in the same thing. So maybe some school they drop. We have no experience. I don't know. Okay. So those ones they are added. You know, I'm not sure for which session they added, but basically we have only open space for Thursday. Now you say 11. 11 is 3 more than what we have. You know, and maybe some people they dropped out from the other you know, sessions. You know, you are in. You know. But so that's good. You know, you talk to Arnold to arrange your lab, you know, to make sure, you know, I don't know, one of the groups, you know, mostly Thursday, you should go there. If you want to switch, you need to find somebody in the other group to switch your class. You know, don't talk to Arnold, don't talk to me. It's really all you. If you find somebody to swap your class, for example, you come, I don't know, Monday, if somebody comes Thursday, something like that, do it. But if you can't find anybody, me and Arnold cannot do anything for you all. You know. These people, they are there, they are there. You know, you should do it. Any question about the first homework? Looks like we forgot to put for figure 2, we forgot to put the load value for load 1 and load 2. Funkfei is going to send you an email tonight, give you those values for load 1 and load 2, and we will upload the new one with the corrected, you know, values for the load, you know, to the website.
For problem 1, it says a balanced 3-phase 208 volt source. Is the 208 volts, is that RMS?
Yes, we talked about this for last, I think maybe this discussion session. We said by default, when we give a voltage, is a RMS. The three-phase system is a line voltage, unless we will specify this is, for example, phase voltage. For example, in the homework one, it said 208. You know, it's going to be 208 line RMS voltage. These are the default things for the. For AC system, when they give you a voltage, by default is RMS. By default is RMS value. Unless we say this is the maximum value, I don't know, whatever, we say something else. If we don't say anything, not usually, 100% nobody say anything, it's an RMS value. For three-phase system, if again they give you a voltage or current, it doesn't matter, you know, this is for both of them. They don't say anything, these are line voltage, line current, and RMS value. Okay, any question? We need to set the exam time, you know, the sooner the better before everybody else will set up the exam time. But, you know, let me think about it, you know, maybe Tuesday we'll set, you know, which day we're going to have the midterm. I think we went through the introduction of the magnetic circuits, you know, we talked a little bit about P, B, H, BH curve, I don't know, inductance, those kind of things. Now we're going to start with transformer. Transformer, we'll start with the ideal transformer first. We went through, I think, 2 examples, you know, Tuesday. Go check those out. They are very helpful for the homework, so you are going to go over it. And we review also the last one we didn't solve because we went through it, you know, how you use the neutral point for solving the problem similar to the last question, you know, the last question. Last question has, it looks very big circuit. but as soon as you put it on the single phase case, it's going to be much more easier to solve it. Still, it has lots of calculation, but the calculation is going to be maybe 20% of the full three-phase system. Okay. We are going to start with the ideal transformer. Looks like I'm moving on my mark now. We are going to start with the ideal transformer. We are going to talk about the single phase transformers. Maybe next week, by Thursday I'm not here, but if I was here Thursday, we'll go up and we'll get to the three phase, circuit transformers. Your midterm, I believe, is going to be until end of the transformers. The material we're going to cover in the transformers, that's going to cover your midterm, exam. And after that, it's going to be the final exam. See, I think most of you have seen transformers already, at least in the paper. Let's call this one I1, V1, transformer, they have a 2 winding, but they could have a 3 winding, they could have 4 winding. We will see those one later. We are not going to discuss about it in this course, but they could have as many as winding they want. But the most common one, they have a 2 winding. They call this one, for example, primary. This one is secondary. So I'm going to go back to the last topic. We talked about it in the Tuesday class. If I wanted to write equivalent circuit of this system, see, I want to see how this system works. See, first let's get the flux. If I put my 4 fingers here toward this current, this winding is going to generate a flux like this, right? This is going to generate a flux like this. Here, I put it such that they're going to help each other. This one also is going to generate a flux like this, right? So both are going to help. Let's call this one flux, right? When you have a wire, let's say you have an electrical wire, you have a DC source, and this is the wire, and you have a load here, right? Let's say 10 ohm, I don't know, 100, right? You see 100 amps, sorry, 10 amps, right? You see 10 amps. This is an ideal case we are considering. What is the non-ideal case? So we assume this resistor, this wire here, it's a perfect resistor, right? Perfect conductor. There is no resistance, right? But in reality, if you look at it here, this one has a tiny resistor, right? Right? And we have air here also, right? Air is a huge resistor, right? Right? I put it this way. Basically, the current coming from here, this source, can go through this wire or can go through here, right? This is like a 2 parallel resistor, right? When we have a 2 parallel resistor, they can share the current. But because this one is maybe a million times more than this one, right? Or I don't know, maybe 10 million times bigger than this current is not. It's very close to perfect, you know what I'm saying? But in reality, it's not. There is a little bit of current, right? Something I will tell you, if you can try, once there is is raining, Go check this one. When one rainy day or it's a foggy day, just there's enough fog in there. Go look at these transmission lines. You have these towers and they have these wires here. These are the big wires going from tower to tower. Sometimes you can find 100 kV, something like that inside the city. If it's not, because during the day you cannot see it, If you go look at these wires, these are like 100 kV, right? And there is a current, I don't know how many amps current is going through this one. If you go look at here, you see a kind of, blue light around this one. Very, very kind of, weak, blue light around this cable. This one is because of the water or fog in the air. The air is going to get a little bit conductive, a little bit, not a lot. What is going to happen? This leakage current here I'm talking is going to start to go like this. The current will start to leak here, right? When the current leaks, it's going to generate heat and those kind of things. And part of it, like an old bulb, they're going to convert to the light, right? So my point is, if you look at the high voltage system, they call it corona. This phenomenon is called corona. Those when they work with the transmission line, those kind of things, they will see this one. It's because of the leakage current. That's why I want to give you an example of what is really happening. You can see the very good leakage current. In this case, nothing. Right? You don't see anything because it's very, very, very small. Now, why did I talk about this one? Because, come back here. If this core is not ideal, what does it mean? There is a reluctance for this core, right? We talked about this one. We can model the core, magnetic core, with a magnetic resistance, right? If this one is not ideal, and it has some magnetic resistance, which it has, some of it, the flux is like a current, right? Some of the flux is going to go from here. Some of the flux is going to go from here. It's going to be direction like this. Or here. There is the air in both sides, right? They call this one leakage flux. Leakage flux. If the core is ideal, what does it mean? The reluctance is zero, right? Like this case. You see, this wire is perfect conductor, right? So no current is going to go here. All is going to go through this wire, right? If the core is, let me call it, they call it CL1. Let me call it, they call it CL1, and this is a CL2. And they call this one CM. They give it a M because it's called magnetization flux. They call it as a magnetization flux. It's not maximum magnetization flux. So if the core is ideal, so basically the reluctance of our core is zero. The reluctance of the core is zero, and basically, which means Pl1 is equal to Pl2 is equal to 0, right? There is no leakage flux. All the flux is going to go through the core, right? Now let me draw the magnetic circuit for this circuit. Equivalent magnetic electrical circuit. We said we'll put a source wherever we have an N and turn on current to put the Ni, the voltage source. So there is one over there, one here. The polarity is going to be, we'll put the forefinger towards in the current direction. So the positive is going to be up here. Negative here, this is the N1, I1. How about this one? It's going to be like this. So the positive is going to be down here, N2, I2. And core has the RC, right? And basically, if I'm going to show those things, it's going to be, this is the RL1, and this is the RL2, right? If the core is not, if the transformer is not ideal. There are a leakage resistance, right? Magnetic resistance. Which in this case, RL1 and RL2, RC is 0, RL1 and RL2, they are how much? 0. They are infinite, not 0. If they are 0, then all the flux is going to go there, right? For the ideal case, right? Now let's write a case here. These two, I'm going to ignore them right now. So the circuit is going to be like this, RC. And we have this magnetic flux, right? I'm going to write a KVL here. If I write a KVL, it says minus N1I1 plus RCPM, right? Minus N2I2 is equal to 0, or N1I1 minus, right? N1I1 plus N2I2 looks will be RC, right? So if RC is 0, basically we're going to get N1I1 plus N2I2 is equal to 0. Or we can say N1 over N2 is equal to minus I2 over I1, right? Keep this one. We do one equation. I assume the transformer is ideal. I found this equation, right? Now, let's look at it here. There is an induced voltage here, E1, I call it E1, and this one is E2. Right now, I assume the transformer is ideal. Means even these wires, they don't have any resistance, right? When we say ideal, we are ignoring the resistance of the couple. We ignore the resistance of the magnetic core. We ignore the resistance of the copper also, right? So based on Faraday's law, I have a winding here. It has N turns, and there is a flux going through here, right? How much is the induced voltage? Faraday's law. E1 is going to be d lambda 1 over dt, and E2 is going to be d lambda 2 over dt. What is lambda 1 and lambda 2? We talked about this is the N1 phi1 and N1 phi m in this case, and lambda 2 is N2 phi. Remember we said flux turn, right? I have a phi m going this way, but how many turns I have? How many turns I have? N1. So basically, the flux turn is going to be N1 times phi m. Here I have an N2. The flux turn for this side is going to be N2 phi m. Now, let's put it here. E1 is going to be N1 d phi m over dt. This one is going to be N2 d phi m over t, right? Let's add a little bit of resistor here, R1 and R2, right? R1 and R2. So here, what is going to here give me? Let's divide them by each other. From these two, I'm going to get E1 over E2 is equal to N1 d phi m over dt over N2 d phi m over dt, right? This one is going to cancel this one. E1 over E2 is equal to what? Is equal to N1 over N, right? Right? Now, let's see what's the relation between V1 and E1. If you look at here, E1, right? If I write a KVL here, minus E1 plus R1 I1 plus E1 is equal to 0, right? So basically, V1 is equal to R1 I1 plus E1. How about V2? Again, the same thing here, right? V2 is going to be equal to R2 I2 plus E2, right? R1 equal to R2 equal to 0, right? Ideal transformer. The copper doesn't have any resistance, right? So it's going to result in what? V1 is equal to E1, E2 is equal to E2. So from here, we say V1 over V2 is equal to N1 over N. We have number 1 equation here and number 2 equation here. 1 and 2 is said for ideal transformer. This is, keep in mind, this is the ideal transformer. We assume the RC is 0, the magnetic core resistance is 0. We assume the copper resistance is also 0. So if we add down, we say V1 over V2 is equal to N1 over N2 equal to minus I2 over I. This is the equation for ideal transformer. Any questions? Yes.
What is E in this again?
It's an induced voltage. Induced voltage. Whenever you have a winding and there is a magnetic field, if you want to practice, you do this one. You know, it's a very simple practice. You get a magnet, a simple magnet, and put a winding, you know, like that. You don't need to have a core here, you know. Just connect it to a voltmeter, you know, the one can measure small voltage. They start to move the magnet. You'll see there's going to induce voltage in the winding. So here is different. You know, we are not moving the magnet, but we are changing the flux. Flux is becoming, either you can move it by your hand, or you could have something is changing internally. You know, this is the internal change. You know, we are not moving the core. In an electric machine, the magnet moves, but in transformer, no, they don't move. Now, this part, I could get it another. You know, I could go through here from another way. Look at here. If I put a box around this, if I put a big box around this, right? I'm going to look at the box. It's not like this. I'm going to use the power equation to get part of this. I have a system like this, right? This is the R1. If you have a question, you can ask me. You don't have to ask your friend. Right? You can look at that, everything put in that green circle, right? It's going to be something like this. Can somebody tell me what's the equation here? Can you tell me what's the power equation here? You are sending power in. You are sending power in, right? Always. Generation should be equal to consumption, right? Always is like, you cannot generate 10 kilowatt and you don't use it. You have to use it, right? So if you look at here, most of them, they are putting the power in this box. So this one is going to be V1 I1 plus V2 I2, right? How much is going out of this box? 0, right? These two, they are coming in, they are putting this much power in. Think about it this a different way if you don't understand. Think about it this way. You have and there's a valve here. You are putting water here, W1, and you are putting W2 here, right? And let's assume this one is kind of, you know, the water level cannot go up. You know, you can go up, you are storing the power, so there's water here. And here the water is going out, right? And this level is fixed, is not changing, right? The level of water is not changing. What does it mean? Whatever is coming in, right? W1 plus W2, they are coming to this tank, right? and W3 is leaving, right? If this level is not changing, it has to be equal, right? Has to be equal. So here, this one is putting power here, this one is putting power here. V1 I1 plus V2 I2. What is going now? Nothing. So basically, V1 over V2 is going to be minus I2 over I1. That's it. You could have done this one with a power balance. What's wrong with, not wrong, what doesn't make sense with this system? Not putting power both in, see what it goes on, right? So one of them should be, the direction should be wrong. Not wrong, you know what I'm saying? This is a, so basically, to correct this minus, if I change the direction of current here for I2, so the current going this way, right? So I'm going to redraw it again. If I put this transformer like this, I1, V1, but if I put the current I2 like this, right? Instead of entering, leaving, right? What is going to be the equation? It's going to be N1 over N2 is equal to V1 over V2 is over I2. There is no negative in there. There is no negative. So these are equations. Most of the time, they show you the books like this. They put, for example, dot here. See, there is a dot. Maybe last year you already did the book. So this one is the V1. This is the I1. I2. I'm going to put this one V2. What does it mean, this dot? So let's follow this dot and know what does it mean. If here is positive, means this dot is positive, right? If I put the dot here, means here is going to be positive. If I put this dot here down here, here is positive, here is going to be positive, right? This is the AC current, AC voltage. Sometimes it's going to be positive, sometimes it's going to be negative, right? So if the wherever the positive for wherever this dot is positive, this dot is going to be positive too. So this is just a kind of a standard for polarity and those kind of things. So if I put this one here, you can see if this one is positive here, negative, right? This dot is going to be positive, so positive, negative is going to be like this, right? But if I put the dot down here, this one is going to be like this, right? If I put it down here, see, when this one is positive, this one is positive, right? When this one is negative, when this one is negative, this one is going to be negative too. I mean, this dot just shows the polarity. That's one. Let me put it back where it was. Now, the other thing it does show is we call it ampere turn law. Ampere turn law. This is the N1. This is the N2. We say those ampere turns, the current enter to the dot, summation of those ones that are entering to the dot, is equal to the summation of those ones that are leaving the dot, right? So here, which one is coming to the dot? This one, right? N1, I1 is equal to. Here, which one? This one is leaving the dot. Those ones that are coming to the dot, they are equal to those ones that are leaving the dot. So it's equal to N2, I2. Let me give you one more example. This is two winding is very simple. You don't get a little bit difficult board. I told you already, transformer they could have as many as 1 you want, right? How? Let me show you first. Really how it's going to be. Let's put a core here, right? One winding here, one winding here, one winding here. Just I want to tell you, this is not the kind of crazy thing. It's, oh, how it can happen. This is a transformer with five windings, right? They have a flux here to share all of them, right? The equation always is going to be correct for all of them. For example, this one is a V1, N1, V2, N2, V3, N3, V4, N4, V5, N5. I'm assuming all the dots are okay. You know what I'm saying? This is always correct. V1 over N1 equal to V2 over N2 equal to V3 over N3 equal to V4 over N4 is equal to V5 over N5. If you had two transformers was this much, right? Look at that one over there, it's the same thing. Just like put the ends over on the other side, right? But if you have more than one, you write it this way. More than two, you write it this way, right? How about the current equation? Would be correct? I1 over N1 equal to I2 over N2, I3 over N2. It is not. Why this one is correct? What does it mean this one? Can you remember this one? This is a dPm over dt, right? Remember we said E1 is dphi over dt, n dphi over dt, right? And V also equal to E, right? Basically V over n is a dphi over dt. All these guys, all these windings, they share the same flux, right? The flux is going through this core, right? So for all of them is a dphi over dt. That's the reason this equation is called. But for the current, no. For the current, you have to draw the magnetic circuit. You said N1 I1 plus N2 I2 plus N3 I3 plus N4 I4 plus N5 I5, I don't know, equal to R times phi, right? If the core is ideal, adding all of them together is going to be equal to 0. But this is under assumption all of them they are generating flux in the same direction, right? Some of them they can generate the flux in the opposite way, right? Now, I'm going to go back to this dot concept. You know, let's say we have a transformer like this. It has 5 windings, right? Like the one I put it here. I'm going to go with this dot here, for example, this dot here. I don't know, this dot here, this one here, and this one here. I put the dots like this, right? So, I'm going to start with this one. This is a V1, I1. Right? N1. N2. N3. N4. N5. Right? Let's put the currents, you know, whatever you want. I2. I3, I'm going to put I4, I4, I5, right? I'm going to stick with the dot for the voltages to see how it is. So if this one is a positive here, V1, where is the V3 positive? See, this one is connected to positive here, right? So this is the V3 positive. If you want, you can put it reverse. You know what I'm saying? If you want, you can put a positive here, negative here. But what's the relation between these two? It's going to be V1 over V3 is minus N1 over N3, right? If you put the positive up here for this one, you say, hey, I don't want to follow your rules. You know, I want to go with my rules. I want to put the positive here. Just be careful. Yeah, you can do that. There is no problem with that. But your equation is going to be this. Minus, right? But if you go with my rules, you know, always there is no minus. You know, always you have the V1 over V2 is the N1 over N2, right? Now, how about this one? Where is V4? Right? How about this one? Because I'm going with this dot, right? This positive. How about the V2? These two also they are the same thing. This positive is here, so this positive is here. V2, right? So this way, if you write it, V1 over N1 is equal to V2 over N2 is equal to V3 over N3 until V5 over N5, right? This is the voltage equation. We can say V1 over N1 is equal to V5 over N5 for this circuit with a 5 winding, right? How about currents? Currents, we go with this ampere turn law, I said. We said for those winding, the current is coming to the point, summation of those ones, Ni, should be equal to those ones that are leaving the dots, right? Let's see which one is coming to the dot. This one is coming to the dot, this one is coming to the dot, right? See, the current is entering to the dot, right? The current is entering to the dot. How about here? This current is going this way, right? Basically, it's like this, right? This one is leaving the dot, right? This one is leaving the dot. How about this one? This current is going like this here. Basically, here is like, again, this one is entering to the dot, right? How about this one? Is leaving the dot, right? So, this one, and this one, the current comes to the dot, right? And the other two, the current is leaving. So, basically, it's going to be N1, I1, plus N2, I2, plus N4, I4 is going to be equal to N3, I3, plus N5, I5. We have these two equations. That's for voltages, this is for currents. And these are for ideal transformer, an ideal transformer with 5 windings, right? Any question about the ideal transformer? Before jumping to the real transformer, I want to go through the impedance transfer in the transformer. Is this one clear?
I still don't really get the current, how you see that's going into,
Here. This is a dot, right? This is a, let's first define when we say enter, what does it mean, and leave, what does it mean. I thought maybe that one is clear. I have a winding like this, right? And the current coming here. This one is entering here. Entering to the dot, right? If I put this dot here, right? This current is going to come here and go like this, right? This one is leaving the dot, right? So that's why I got my definition of entering and leaving the dot. Any other question? Okay. Before going to the real transformer, impedance transfer. The title will be impedance transfer. Let's say we have an impedance here, ZL. I want to see how much is the Z in here. I have a ZL, I don't know, whatever ohm in my secondary, right? I want to see how much is this impedance if it comes to the primary. Let's write the equation here. Here, ZL is equal to V2 over I2, correct? The current is I, the voltage is V, right? V divided by current, voltage divided by current is the impedance, right? Now, let's see. Based on what we have here, this is the ideal transformer. We know V1 over V2 is equal to N1 over N2. And we know I1 over I2 is equal to N2 over N1, right? So, before going going ahead. Z in is a V1 over I1, right? If I want to find out how much is my impedance here, right? So this voltage divided by this current, right? You know this in circuit theory, right? We call it input impedance, right? You say the voltage divided by that current is going to be Z. We define it input impedance or output impedance. You know those from circuit theory. So this equation will tell me V1 is equal to N1 over N2 V2. And this equation tells me I1 is equal to N2 over N1 I1, right? I want to see, the question is, I want to see how much is the input impedance in this circuit. I know in my secondary I have ZL. I want to see how much is the equivalent of this one coming to primary. Now, let's replace it. I'm going to put instead of V1, I'm going to put this value. It's going to be N1 over N2 V2. Right? I thought this is for I1, I'm going to put this value, N2 over N1 I2. Right? This one is going to be N1 over N2 to the power of 2 times V2 over I2. Right? How much was the V2 over I2? ZL, right? ZL. So basically, Z in is equal to N1 over N2 to the power of 2 ZL. So it's making movie over there. You don't have to take a picture. All is going to be there. There's the class website if you want. You uploaded already okay. Anybody has checked it to see it's good or not?
I checked it, it's great.
Check you're on the classroom, the class website. If you don't have a class website, just send the email to Arno. Arno will give you a password. You can log into the class website, and the homework solution, not now, but after you turn it in, solution and the class, presentation will be there. So basically, if I want to name any impedance, could be inductor, capacitor, resistor, whatever, Z. If I'm going to bring it from this side to this side, so what does it mean here? It's going to mean like this. It means you can get rid of the transformer. Hey, there's no transformer. I have a V1, I1 here, and this one is going to be N1 over N2 to the power of 2 Z. So if I want to know how much is the equivalent of this resistance in secondary, in my primary, what should I do? Wherever I'm going to this side, N1 over N2 to the power of 2 times this, right? If it was the other way, if the impedance was here, and I want to know how much is there. How much would, if we have a ZL here, how much is the impedance here? N2 over N1 to the power of 2 times the ZL. Wherever you go, for example, if you go to primary side, it's going to be N1 over N2. If you go to the secondary side, it's going to be N2 over N1. Wherever side you go, that one is going to be, the number of turns is going to be in the numerator. It's going to be, in this case, because we are going from secondary to primary, it's going to be N1 over N2. If my circuit was like this, if I had like this, so basically this one would be equal to this. And how much is this value? N2 over N1 to the power of 2. And this is the N1 and this is the N2. Right? My point is it could work either way. You can go from primary to secondary, or you can go from secondary to primary. It doesn't matter, Either way it goes. Let's go through a simple example. a circuit like this, I'm going to put it gel box. This is the circuit theory, not this course, but this is the N1, N2. And by the way, for the impedance doesn't matter where is the dot. You know what I'm saying? For impedance doesn't matter. Don't worry about where is the dot. Wherever it's going is going to be N1 over N2, or N2 over N1. Here we have a Z2. And here we have another transformer is N3, N4. And here we have a Z3. I want to know how much is the Z. I want to know how much is the Z. Right? I think you have this one in the second story, right? Did you? ECE188? No, this is not mutual inductance. Mutual inductance will let me express this far down, but this is not mutual inductance. So let's forget this part for now. Let's assume this part is. I'm going to start from the very end here and come toward this. Let's forget that part. We don't have that part, right? If I want to bring this one here, how much is the equivalent of this one here? How much is the equivalent of that? I'm going to put it with a green color. So basically, it's going to be impedance here. I'll call it Z prime 3. This is the equivalent of this one. How much is Z prime 3? It's going to be N3 over N4 to the power of 2, right? Now, these two, they are in series, right? These two, they are in series. So basically, my circuit is going to be like how much is this value? Right? These two impedances, they are in series. See, this part is not anymore there, right? I value of this part. I brought this one here, so this one is gone, right? So these two, they will be in series, right? So the impedance is Z2 plus Z prime 2, right? Now again, forget this part. Forget this Z1. If I want to bring this one here, how much is this one? N1 over N2 to the power of 2 times this impedance, right? Let's put it there. We're going to have another impedance here. How much is this? It's going to be N1 over N2 to the power of 2 times Z2 plus Z. Let's call this one Z prime 2. I'm going to call it Z prime 2. Right? So basically, my circuit is going to change to this. This is Z1, this is Z prime 2. How much is the Z in? Z1 parallel to Z prime, right? It's a simple example for impedance transfer. Doesn't matter. Except for the impedance doesn't matter. If we will find out voltage, yes, they will matter. But for impedance, they doesn't matter. Any question? real transformer. So when we say real transformer, what assumptions are going to be gone?
That there's no reluctance.
Core is not ideal anymore, right? First. So there is a leakage flux, right? And copper is not ideal, there is a resistance in the circuit, right? Before we start the model for the real transformer, let me just remind you of something here. A quick note. If we have a core, this is a ring. I call all these together, I call it field leakage. You know, I'm going to go with one winding first. You guys will figure out that one. And after that, we go to the two windings for transformer. This is a real inductor. You have a real inductor. It's basically inductor. It's not transformer. Transformer means we have to have two windings, right? If there is a magnetic core and a winding, it's basically an inductor, right? Just I want to write the KVL here. First of all, phi for this one, the total phi going through this one is going to be phi m plus phi m, right? There is a phi m going, and actually, let's put it this way because we are going to get confused. Let's put this one phi l over 2, and this is a phi l over 2. Right? Half of the flux leakage is going that way, half of it is going this way, right? So basically, how much flux is going here? We have phi m, right? We have phi l over 2 coming, phi l over 2. So the total, we're going to have a phi m plus phi m, right? Now, sometimes that to make it easier for drawing, we assume here there is no leakage. We will put all the leakage here, you know, just for drawing purposes, you know, not reality. Reality, both sides there is a leakage, you know what I'm saying? So phi is a phi m, the flux going through this winding is phi m plus phi m, right? How about E? Let's do this. Lambda is n flux, right? It's going to be n phi m plus n phi m, right? Lambda, flux term, is the number of terms times whatever flux is going through this one, right? Now, E, the induced voltage, is equal to d lambda over dt, right? D lambda over d, or is equal to n d phi m over d plus n d phi l over d. Because I'm writing all the equations for this simple circuit. And the last equation I have here, V is equal to Ri, R is this resistance. Let's not make it smaller to not make a mistake with your reluctance. Let's say this is R, I'm going to put it here. Ri plus E, or is equal to Ri plus d lambda over d. Right? So this is all the equation for this simple circuit. Now we are going to go to the real transfer. question here? You need to understand this one too. We're going to go through the rest for the two windings, you know. Any question here? Lambda is the flux term. This is the Faraday's law. I think you had it in physics, right? You know, one of the very first course you have is the physics. You talk about, they call it physics electricity, I think, something like that. You go through the Faraday's law and those kinds of things, right? Lenz's law, Faraday's law, those laws. This is the Faraday's law, you know. When you have a winding and the flux, the induced voltage is the derivation of the flux over the time times the number of turns, right? You have seen this equation before, right? You haven't seen this one before? How many of you haven't seen this equation? E is equal to NTP over D. How many of you haven't seen this one? You haven't seen this one? Which year you are?
Some kind of weird senior.
You are senior and you haven't seen the Faraday's law, you're getting the electrical engineering degree. Because the Faraday is the father of electrical engineering. They call him the father of electrical engineering. And you are in senior year and you haven't heard about the Faraday's law. If you would tell me I'm a freshman, I think maybe yes. But senior is a little bit.
I've heard of Faraday's law, but I didn't see it like an equation form, or I can't remember it back in time.
Okay. Anybody else? The way I behave, nobody tells me. No, really, anybody else has? Don't worry, no, because it's really strange for me, a senior student, you know.
To be safe, I'm just going to say that I'm not comfortable with it. Maybe I've seen it, but I'm not comfortable.
You didn't like it?
Just a question, do they always use E? I feel like. Yeah.
Usually use E. I haven't seen to get anything else, but this is all names. You know, if you want to use something else, you can, but usually they use E for it. Okay, so by the way, this is the Faraday's law. Faraday's law, very simple. It says, just going back, remember in this rule we had a BIL, I don't know, F is equal to BIL, there was another BL, I forgot the other one. It said that there is induced voltage. You had it in high school physics. I had it in high school physics, you know, this kind of thing. You said the induced voltage is a BMV, remember that? B times, not BMV, BLV, B times L times. You said if I have a magnetic field, let's say I have a magnetic field like this. Maybe I'll say this way, you remember something, you know. You have a magnetic field, it's coming out of, you know, the board, right? And I have a conductor here, right? Length is L, right? And we say this one is moving, for example, with a speed of V, right? We say the induced voltage is V, L, V, right? This is the Faraday's law. This is the Faraday's law. It's coming from the same equation, which is dq over d. This is the induced voltage in a conductor. And if the other one was the, we'll go through this thing in the energy converter. It's the basic of electric machine. When you have a generator, you're going to generate voltage. When you have a motor, you're going to generate torque or force. The other equation, if you remember, was the BIL. So F is equal to BIL, if you remember that. From, I don't know, high school, whatever. It was a BIL, right? The force was the other. These two, they are the basics of generator and motor, and in general, electric machinery. These two equations, these two equations, they are the basic of electric machinery. Now, let's go to the real transformer, right? We have a two winding. I'm going to put the number of turns later to see where I felt completely. Anyway. Let's call this one E1. Call this one E2. And this is the N. treat each winding independently from the other. Okay? So if I had only winding number 1, right? Look at here, the flux is going to be like this, right? The flux is going to be like this. So I'm going to have phi m1. This is only generated by winding number 1. There is no not winding number 2, right? Like the one I put in the board here. Right? And you are going to have some leakage, right? I just put it on this side here. I didn't put it inside. As I said here, it's going to be on both sides. But just for drawing, sake, to be easier to draw it, I put it on the left side. I have this one, right? Leakage. And R1 is the resistance of this winding, R2 is the resistance of the other one, right? Now, let's forget winding number 1. We have only winding number 2, right? We have only winding number 2. So the current is like this, the flux is going to be like this, right? The flux is going to go like this. So I'm going to have a flux, I call it phi m2, right? So magnetization flux is because of both of them, right? The total magnetization flux is going to be phi m1 plus phi m2, right? The way I put it, they're adding together, right? Here also, I'm going to have phi m, right? Is it clear here? I had 2 windings, I treat them separately. The one is going to generate the phi m1 and phi l1. Number 2 is going to generate phi m2 and phi l2, right? Now, let's call the total flux for the winding number. See what I did here? Look at this. Let's go back here. I calculated the total flux here, right? Because I need to go to the equation of voltage and those kind of things, right? So I need to calculate the total flux. How much was the total flux? It was the phi m plus, this one is coming this way and this way. It was the phi m plus phi l, right? Let's calculate the total flux for each winding. How much is the phi 1? Somebody tell me, how much is the phi 1?
Phi m1 plus
Okay.
Phi
Tell me, phi m1, okay?
plus Phi l1
Because I'm not writing it because I want to put it in kind of specific order. But tell me, phi m1 plus
plus Phi l1
phi l1. Okay, I'm going to write phi l1 first. Phi l1 plus phi m1. Okay? Anything else? Now most of them divided. See, both of them divided circuit, right? It's a transformer. We have both winding. Both winding, they have a current. Is there anything else? I think this is good. How about phi 2? Phi l2 plus phi m2. Everybody agrees with this?
Shouldn't that be mutual inductance?
Everybody disagrees with this? So everybody not agree, not disagree, but you have to be one, right? You have only 2 choices, yes or no. This one is correct?
Yes. Shouldn't there be
Why?
mutual? Shouldn't there be mutual inductance?
That's it. Those one you're saying yes. Why? One of you can say yes. Tell me why is correct. First, let's figure out what's the phi 1. Let's understand what's it. Phi 1 is the total flux going through this winding, right? Okay. I get it. Somebody say, oh. Okay. What we are missing? Phi m2, right? If you look at here, there is a phi l1 going up, right? There is a phi m going up, and there is a phi m2, right? So we miss phi m2. How about here? Phi m1, right? So look at it. Phi m2, phi m1, and phi m2, right?
If the leakage current, sorry, the leakage flux is large enough, the leakage
before that one happened, is saying, can it happen, for example, like leakage of this one comes here? You know what I'm saying? Yes, it can. Really, yes. But think about it, if you go from this leg to that leg, so this core should be really bad core to have lots of leakage, you know, to go over there. Yes. And still in reality, there's a very, very, very small leakage coming from there, but yes, it's almost zero, you know. That's very, very small. Very good question. Now we know the flux for each of them. I can start to go through this thing to figure out how I can come up. My goal is to come up with the equivalent circuit for this transfer. How much? 10 more minutes? I have to go really fast. Okay. Let's do this. How about lambda 1? So how much is the lambda 1? Is n1 phi 1 and lambda 2 is n2 phi. Check the left side of the board. Lambda is equal to n phi, right? So basically this one is going to be n1 phi l1 plus n1 phi m1 plus n1 phi m2. This one is going to be n2 phi l2 plus n2 phi m2 plus n2 phi m1, right? Something I forgot to say. Remember we had in the Tuesday class, something I forgot here. If I want to calculate L, how much is the L? L was lambda over R, right? That was the definition of L. If you go check your Tuesday note, you know, it was it said the inductance definition is lambda over R. Basically, in this case, let me finish this one. No, I should have it. So in this case, it's going to be n d phi n, sorry, n phi n over I over I plus n phi l n phi l, sorry, phi l over I. We call this one because it is because of the magnetization flux. We call this one Lm and this one Lm. This one we call it Lm and this one we call it Lm. This is a magnetization inductance. Why? Because it's created by magnetization flux. The flux is going through the core. We call it magnetization flux. This flux changed this material to be a magnet. We call it magnetization flux. This flux is going through there, is a leakage. We call it leakage inductance, magnetization inductance, right? Now, I'm going to go back. Now, I'm going to calculate the lambda one. Let me do one more thing here because if I make this equivalent circuit for this circuit, it's going to be like this. It's going to be a source of Ni, right? A source of Ni, a resistor of Rm. Rm is related to the core, right? Rm, the length, right? Rm is going to be what? Lm over mu A. A is cross section out here, right? L is this length, average magnetic length, and mu was the permeability of this core, right? Do I have any other resistor in this circuit I'm missing? Whenever there is a flux, there should be a path, right? Here also there is a resistor, right? So if I'm going to show you, it's going to be like this. call this one RL. The leakage reluctance, right? How much is the RL? RL is difficult to do. Let's call it, I don't know, LL, or it's going to go through the air, right? It's going to go through the air. It's going to be mu0 and AA, for example, something. This one is very difficult. You have to do the final element to get this number, you know. But you know, just I'm putting it as simple here. So how much is the phi L? If I want to calculate, this is the phi L, right? And this is the phi N, right? How much is the phi L? How much is the phi L? Ni over RL, right? How much is the phi N? Is Ni over Rn. Alright? You guys need to follow this one first to understand it because it's too winding. Exactly copy of this one. But that one is for a one winding, you know, real winding. With the leakage flux and with the resistance, right? Now we can go back. Now we can go back. So I'm going to replace this value. I'm going to replace this value. Again, before going to here, let me see. I'm going to come back here. If I want to write this one more time, let me continue this one. L is going to be, I'm going to replace Pm with this value, right? Is that if I put the Pm over there, it's going to be N squared, right? Over Rm, right? Yes, N squared over Rm plus N squared over Rn. Just replace the phi n with that value, replace the phi l with this value, right? So this one we said is Ln, and this one we said is Ls. Leakage inductance, magnetization inductance.
What is RL? Is that like an induced
No,
loss?
RL is kind of, you know, imaginary, to put it this way, imaginary number, you know, fake number, to model the resistance of, the magnetic resistance of the air.
Okay.
Because it's very difficult to come up with a number. But there is a number. I don't know how much is it, just I put RL for it, right? Yeah, that's the number, you know. If you want to calculate this thing, you know, I'm not sure, I don't think so, you know, you're familiar with finite element, but this thing you can do to finite element, it's going to give you a pretty accurate number, how much is the RL. But analytically, it's impossible to solve. And most of the time, we ignore it. We say it's zero. It's infinite. It's infinite. It's infinite. Now, I have this one. I want to rewrite this equation. I want to rewrite this equation. Now, lambda 1 is going to be, here. Let's call this one equation 1. Hold on. Let's summarize something here. Okay, how much is going to be? I'll say this for now and finish. Okay, based on what I said here, forgive me. Tell me how much is the phi L1? How much is the phi L1? How much is the phi L1? It's going to be N1, I1 divided by RL1, right? That's what I did here. Here I didn't have a 1 or 2, so I think I had only 1 I did here. So phi L1 is going to be N1, I1 over RL1. What is the RL1? The magnetic path over here, right? Equivalent magnetic path, resistance of this magnetic path, right? How about phi M1? How much is phi M1? Let's say this core, right? the magnetic path of this core is Rm, right? Let's call this one Rm. Like here, I call it what? I call it Rm, right? The magnetic path is this one. I call the reluctance of this path Rn, okay? So phi m is going to be N1 I1 over Rn, right? How about phi L2 and how about phi L2 and phi M2? You tell me. How much is the phi M2? Phi L2. N2 I2 over Rn2, and this one is going to be N2 I2 over Rn. Let me draw the equivalent magnetic circuit of this one here. It's going to be like this. I'm going to have one source here. Think about this. N1 I1, right? And there is a leakage pass here. This one is RL1 and this is a PL1, right? And my core has a magnetic reluctance of Rn, right? And here, what was the polarity? This is positive, negative. And here, there is another one, positive, negative. This is the N2 I2, and there is a RL2. Just I want to show you how they write those equations. And this is a phi L2, right? Now here we have phi M1 plus phi M2, right? But remember, phi M1 was when only we had the I1, right? If I want to calculate the phi M1, what should I do? I should put I2 equal to 0, right? I said phi M1 is the magnetic flux when we have only winding number 1, right? When we have only winding number 1, how much is this? 0. I2 is 0. So 0 parallel with RL2 is 0, right? Is 0. How much is the phi M1? This voltage divided by this resistance, right? Now, how about phi M2? Phi M2 was the flux when I1 is 0, right? I talked about that when I put this one here. I said let's assume this one is not here, right? Which means the current is 0. The same thing when I was putting this one, I said let's assume this one is not here, right? So phi M1 is the flux when I2 is 0, keep in mind. Phi M2 was the flux when I1 was 0, right? So you can calculate this one like this equation. Yeah, I'll stop here and I'll continue. They're saying why there is no magnetic resistance here. Basically, magnetic resistance, look at wire. If you have wire from here to here, right? This one has a resistance from here to here, right? But to make it simple, okay, I'm going to model it with one resistance, right? I put the magnetic, this one for all this house. Like wire. You have a 100 meter wire, you're not going to put a 100 this wire is 5.
Are you in any other ECE class?